Okay, class, I guess this thing's recording. April 1st, April Fool's Day. I thought we were going to move on and start talking about scattering parameters, right? But I failed to realize that there was a section in between on lumped element matching. Now, some of you have been presented with this material in EMAG 1, right? While I'm covering transmission lines, when I teach EMAG 1, I just pick this topic up then. It seems to be logical to do it then since you're already in tune with Smith charts and the like. Uh, but of course, probably some of you didn't have me for EMAG 1. That's definitely a possibility. So I guess we need to go over this material today and then kind of make sure that you've got a grasp on it. So for some of this, for some of you, this will be review, and for some of you, this will be new material. Okay. All right, and then hopefully Friday we'll move on to scattering parameters. So we had a section there in between that I had just overlooked. So make sure you're reading the book now. Keep up and read chapter 10, and then of course time permitting, we're going to go back to and pick up 9, but we'll see how far we get. Okay, we're making reasonably decent progress considering that we're having to record all these videos and run things back and forth on email. That takes time. All right, to the task at hand, right? Lumped element matching. That's what we're doing. So you're going to read this section. Maybe I'll zoom in a little bit. That might be better. So, right, when we're matching, sometimes we use stubs. The previous lecture was a case where we used a couple of stubs, right? We were talking about impedance with microstrip line, and there was a little example that we worked through with stubs. So you could review that on the previous video. And then sometimes we use lumped elements, right? Just simply L's or C's. Well, the choice of L or C at higher frequencies, you have to pay attention to that, right? If you look at the available circuit elements, some L's and C's are designed to function as L and C's at higher frequencies, and some are not, right? Sometimes we have to pay attention to the lead lengths and things of that nature because that'll modify the value of the capacitance and or inductance that we're using. Right, so typically lead lengths, right, need to be short. Right now, at higher frequencies, even higher frequencies than those appropriate for lumped elements, right, we typically use stubs. But right, the lengths of the stubs are somewhere proportional to the wavelength. So at lower frequencies where the wavelength is long, that's where we're going to use lumped elements, and at higher frequencies where the wavelength is shorter, right, we're going to use stubs. So that's typically the way to think about it. All right, so this is the case where we're going to use lumped elements, right? It's the frequency range where lumped elements or circuit elements are appropriate for matching. Okay. So here's, in a nutshell, here's what we're trying to do, right? Here is the load impedance, right? And it's given. It'll be some value. We're going to work an example in a minute where that's 250 minus J 250 ohms, right? And so we want to use a L network, right? This thing is in the shape of an L, where this is either some inductance or capacitance yet to be determined in shunt with the load, right? In parallel with it. Shunt means parallel, followed by some L or C in series, right? And so we have to choose or pick or determine the values of this inductance and capacitance so that this impedance combination here ultimately is 50 ohms. So we're going to use the Smith chart to accomplish that. So this is the way one does this is via Smith chart. Now, I presume you could do it through MATLAB and do some circuit analysis and approach it that way. I'm sure that would work. I haven't done that, but the Smith chart is certainly a pretty straightforward method of determining the values of L and C necessary to match the known load to a desired input impedance, right? Okay, so why would we do this, right? Well, the reason is, right, whatever power is being supplied to this circuit, if we tried to supply, if we connected the transmission line directly to the load, right, there would be some considerable reflection, right? And so not all of the power available will be delivered to the load. When we put in this matching network, right, now all the power coming down the transmission line that connects at this point is going to be delivered to the load, right? So we've increased the amount of power delivered to the load. So if this is some antenna, we can think in those terms, then the power delivered to the terminals of the antenna now more power is delivered to the terminals of the antenna, and consequently more is radiated into space, right? That's the objective. And so we could pick up the signal from another distant receive antenna further away than we could if we didn't carry out the match. All right, so those kinds of things are somewhat obvious, but it's important to make sure we understand why we're doing what we're doing. Right? So, given Z load, right, determine L and C so that Zn is the desired value, right? It might be 75 ohms or 50 ohms or whatever it is, but typically it'll be 50 ohms. Put ohm symbol there. All right. Now it's possible, right? Let's move down. I'll try to keep this. Sometimes I look back at the videos and I see that I've not done a too thorough a job of getting the sheet where you can see what I'm speaking or speaking to, right? So here, right, we led with a shunt element and followed with a series element. Alternatively, right, it might be required, or it might be an alternative solution to lead with a series and follow with a shunt. Okay, so we'll see. We'll see. And so you don't know in advance necessarily whether you need this topology or this topology. But you can figure that out as you go along, again, using the Smith chart. We'll see how that works. So, and it might be, as I mentioned a moment ago, right? It could be that there's more than one solution. Right? Now, right, on exams and stuff, I usually say something to the effect, make sure your first element is a shunt C, or make sure your first element is a series inductor, right? When I say first element, I mean the element closest to the load. And so that'll force you into one solution or the other. That way I don't have to grade several solutions. But note that there is more than one solution. And, right, depending on other circumstances, one solution may be better than another, right? Because of a couple of things. It could be that one has more bandwidth than the other. Right? That's a possibility. So you might want to choose one over the other. Or it may be that you have some in your cabinet of parts, you might have a certain range of L's and C's, and that range of L's and C's that you have can accommodate one of the solutions, but not the other. So you just don't know, right? So it's a good idea to be able to determine both solutions and pick the one that is most appropriate. Right. Sometimes because of DC blocking, right? A cap will block DC. And so sometimes you either want or want to avoid blocking DC. So one of these solutions might be superior to the other, assuming that there is more than one. All right, let's get on to the task at hand, right? Page 2. Move on. I'll scan the notes as usual and then put the video out on the both the scanned notes and video out on the engineering FTP site. So, right, how are we going to solve the problem? We're going to use a Smith chart. Right, that's the way we're going to do this. So in this, right, I'm going to have to flip back and forth between uh, the verbiage here and the solution on the Smith chart. Let's zoom out a little bit so we can see the whole chart. Okay, so you'd be able to print these out or look at them on your computer and do a pretty good job of ciphering what's being. Yeah, that's better. At least on my computer, I can see it better. Okay, right. So we want to use a Smith chart. So let's just work an example, right, and follow through this example. And this is the example in the book, right? First example in the book. So this would be on this material. Example 10.2, page 551. So Stu goes through it, and then we're going to go through it. I'm not sure whether my solution is identical to his or not. I just didn't look. I just took his problem and solved it. But perhaps his is different than mine, which would be good, right? Because then you'd have more than one solution to the same problem, right? And sometimes that happens, and you'll see why momentarily. Okay, here we go, right? Design an L section network to match 250 minus J 250 to a 50 ohm line, right? And we're going to do the design at 800 megahertz, right? And so at 800 megahertz, the wavelength is 37.5 centimeters. So that's a fairly low frequency, right? So if you're talking about using stubs, these things could begin to get pretty long, right? 37, 40 centimeters is a pretty long stub. So it might be more appropriate and more compact to use circuit elements, right? Lump circuit elements. And so let's figure out what the value of those required circuit elements would be. All right, what do you do first when you're working with a Smith chart, right? You normalize the load, right, to the characteristic impedance. Get this gooseneck down here, so let's see if that helps any. Yeah, that's a little better. So step one, normalize load to characteristic impedance. So our load in this case is 250 minus J 250. The desired characteristic impedance is 50 ohms. So you divide the two and you get 5 minus J5. So now you're ready, right? Now you can get on the chart and draw the SWR circle. So 5 minus J5, right? Real normalized load resistance, normalized load reactance. Fast forward, blah, here we are, right? 5, right? There's your 5 circle, and there's your 5 reactance, minus 5 reactance circle. The intersection of the two puts you right there, right? So right there means being at that location is the same as being at the load, right? And so then what do? Right? Typically, right? And we take our compass, sharp point at the center of the Smith chart, roll out your radius and draw the circle. Okay, so this is again with reference to the previous lecture, right? SWR circle, gamma circle, load circle, whatever you want to call it. So I drew that circle and I tried to make it dark so you could see it. Okay. Now the other thing we're going to need when we do this, right? And recall from EMAG 1, right? That we need that back rotated unity conductance or unity resistance circle, right? The back rotated unity conductance or unity resistance circle. That turns out to be important to us, right? So here's your regular unity resistance, unity conductance circle, right? So I need to back rotate that thing over here. Recall how you do that, right? You put the sharp point on 3 and you extend the radius of the compass out to the origin, right? So that'll trace out the regular unity resistance slash conductance circle, right? Then you come over here and you put a little tick mark, right? Can you see that? Little tick mark. Then you put the sharp point at the tick mark and then swing out the rotated unity conductance slash resistance circle. Some of you are familiar with that. Some of you are not, perhaps. So that's how you do that. You just want to take this and repeat it over here. I did it one way. There's other ways. It's a drawing issue. Okay, so then I've shown this in dark too, so you can see it. So this is the back rotated unity conductance or resistance circle. Remember now, the important thing with Smith chart work is you have to pay attention to whether you are in impedance coordinates or admittance coordinates, right? When we're working in impedance coordinates, we say resistance and reactance. When we're working in admittance coordinates, we say conductance and susceptance, right? So use the right language, pay attention to what coordinate system you're in, okay? If you'll do that, it'll avoid mistakes. Okay, you'll avoid a lot of mistakes if you pay attention to what coordinate system you're in. Okay, so, right, here we go. Now back to this real quick, right? So plot 5 minus J5 on the Smith chart and draw the circle. Also draw the back rotated unity conductance resistance circle. So we've done that much. I tried to divide this up in specific steps. Step 2, move from little z load to little y load. Those are little, not big now, directly across the chart. How do we go from an impedance to an admittance? You just go straight across the chart. Okay. So once you do that, right, we start over here in impedance coordinates, right here. And when I shoot across to here, I'm in impedance coordinates here. Now I've changed over to admittance coordinates. When I'm here, I talk R and X. When I'm here, I talk G and B. Right? My language changes because I've changed the coordinate system. Okay. Furthermore, right? Furthermore, an important thing to realize is no matter where you're on the chart, if you're adding reactance in impedance coordinates or you're adding susceptance in admittance coordinates, plus or minus, right? You are going to move on a constant resistance or constant conductance circle, right? Because if you're adding J, you can't change. If you're adding J in impedance coordinates, you can't change R. That's not going to change R. Similarly, right? If you're adding B or susceptance in admittance coordinates, you're not going to change G. Okay, so because of that, right, you're going to slide along a constant resistance circle or a constant a constant conductance circle. Got to get the language right myself. Okay, so that's a mouthful, but anyway, that's where we are. Right. Plot the load, right? There's Z load right there. Draw the circle. Draw the back rotated unity conductance circle. Go from here, right? Z load. There's Z load right at that dot. Change over. We're going to change over to admittance coordinates. So now I'm over here, right? Through my circle. So, right, Y load here. What is Y load there? It's 0.1, right, plus J 0.11. Okay, 0.1 plus J 0.11. So the load impedance, right, the normalized load impedance is 5 minus J5. The corresponding normalized load admittance is 0.1 plus J 0.11. Okay? So being at this location is the same as being located at the load admittance. Right? So now, right, the next step, right, in this process is to get to the back rotated unity conductance circle. Why did I say conductance, right? Because now I'm in admittance coordinates, right? If over here I were in impedance coordinates, I'd say the objective now is to get to the back rotated unity resistance circle. But no, I'm working in admittance coordinates. So now my objective is to get to the back rotated unity conductance circle. Well, maybe that's making you mad, right? I'm saying it so many times that it's becoming annoying. I hope that's the case, right? That's the intent here is make sure you realize that because that's where mistakes are made. All right, so right, step two, move from ZL to YL directly across the chart. Now you're in admittance coordinates. I'm trying to emphasize that in the writing here too. So we want to go again. We want to get from here up to the back rotated unity conductance circle. So the only way we can make that movement is along a constant susceptance, a constant conductance line. Here, get my language right. Right. So we're going to slide along the point one conductance circle, and we're going to go from here, right, along to this point. So I want to start it here at this location, which again is point one plus j 0.11, and I want to end up at point one plus j 0.3. Okay. So that's what I'm trying to do. So I want to go from point one plus j 0.11 to point one plus j 0.3. So I need, right, I need to add plus j 0.19, right? I need to add a normalized susceptance of plus j 0.19 or an honest to goodness susceptance of 0j plus j 0.19 times y naught, right? I want to unnormalize. And that's equal to, right, a positive susceptance is a capacitor. So that has to be equal to j omega c, right? So now I have a formula, right, that I can use to solve for C. So C is just going to be 0.19 y naught over omega. And there it is, right? Or it is, when you do the arithmetic, it turns out to be almost zero point 0.8 picofarads, 10 to the minus 12, or zero point 0.8 puffs. Some people call them puffs. Okay. So we've made the first move, right? Let's review quick. Load impedance, load admittance. We've chosen to move up to here. Good. Now, is that the only way we could have gone? No, it is not. We could have gone down this way, right? We could have slid down to here, which was about 0.1 minus j 0.3, and that would have required a shunt inductor. Right? Think about it. If I up here, this move required a shunt capacitor. If I had chosen this move, which is another solution now, it would have required a shunt inductor. Maybe you can think through that solution, or perhaps that's the one Stu gave. I don't know. I'll have to go back and look at it. Okay, so we moved up here, right? That's an admittance move, all right? So then what, right? Now we're going to switch back to impedance coordinates. How do I do that? I go right back across the chart, right? So if I got to the back rotated unity conductance circle up here and I switch back to impedance coordinates, then I'm going to be on the unity resistance circle. That's going to put me on a unity resistance circle. How do I know? Well, because I back rotated the unity resistance circle to begin with, right? So that was you have to think through this and see, it becomes clear why you did the things that you did once you see the solution unfold. So some of this is working backward. Okay, so right now switch coordinates. Now I'm down here. Where is down here? It's 1 minus J3. 1 minus J3. What is my objective? My objective is eventually get to the origin, right? Because if I get to the origin, then, right, then it's going to be 1 plus J0 normalized, multiplied by 50, that's going to be 50. So in all of these matching techniques, you can you can say that the eventual objective is to get to the origin through some set of legal moves, okay, without breaking the rules of circuit theory and electromagnetics. So here we are, right? Got up here, came down here, one minus J3, right? So now I'm going to slide along the one circle, right? I can't change, I can't get off the one, right? Because I'm just going to be adding say I'm negative. I need to add a positive. I need to add a positive reactance, right? Need to add a positive reactance to get me from here to the origin. How much do I need? I need to add 3, right? Because that's 3 right there. Is that 3 or point? Yeah, 3. I need to add plus J3 times Z naught, honest to goodness, right? Because I'm negative down here, and uh, to get rid of the negative, I need plus. So I'm going to have to multiply 3 times 50, and that's the amount of J that I need. And so I'm working in impedance coordinates. So that's going to require a series inductor. It's going to require a series inductor to get from here up to here. This required a shunt C. This requires a series L. Okay, this is summarized over here, right? On page 3 in the verbiage. From the position on the back rotated unity conductance circle, switch coordinates to the impedance and land on a normalized impedance of 1 minus J3, right? To get to the origin, we need a series J 3.0 times Z naught, which is J omega L. Solve for L. That's about 30 nanohenries, right? At 800 megahertz, it's going to require about 30 nanohenries. So we got it. We've got the network developed. So draw the network, right? So here's our load, right? Here's our 0.756 picofarads. That's the first element. It is a shunt element. Why? Because we were working in admittance coordinates, and it's followed by a series inductor. Why was it series? Because we switched back to impedance coordinates of 30 nanohenries. So now this is a circuits problem. You have to check to make sure you didn't make any mistakes. That's what we're doing now, right? So let's do the circuit theory, right? Straightforward impedance, equivalent impedance calculation, right? So this impedance right here is 1 over J omega C, which is minus J 263 ohms. This impedance is J omega L, which is J omega 2 pi times 800 times 10 to the 6 times 30 times 10 to the minus 9 is plus J 151. So I need to check the input impedance here, or the equivalent impedance looking into this pair of terminals, right? I need to put this in parallel with this in series with that, right? So it's minus J 263 in parallel with 250 minus J 250, and then whatever that parallel combination is, I need to add J 151 to it. So you see, if you go through the arithmetic, you get 53 minus J3, which is about 50 ohms, and so a little bit of error due to round off, right? A little bit of error due to round off. Make sure you complete this step, right? Check your work. If it doesn't work out, you made a mistake somewhere. Go back and figure it out. Okay? All right, so this is kind of a short lecture, I hope. Uh, some of this was kind of a beating a dead horse on some of these issues for those that are already familiar with the subject, and I apologize for that, but it may be of value to those who are not so familiar with it. So go ahead and work number 23, right? That's problem 1015. And so Stu has a solution back there to that. See if you can get that solution. I can put a solution of my own out there, and I'm to homework number 23. But you know, the answer's in the back of the book for the odd one on this out of this chapter 10, odd problems. And so see if you can match his solution. Right. Work it by yourself in as many different ways as you can, and get the appropriate circuits, and then go back and check. See if you got it right. Right, that'll build your confidence. Okay, that's enough for this day, right? Friday, I guess I'll try to put on the scattering parameter stuff, right? We'll start talking about that. All right. So this lecture was lumped element matching. Some of you have already been exposed to that. If you had me for EMAG 1, if you didn't, you may not have been. You may not have addressed that yet, and so this kind of gives you an example. And then there's additional examples in the text. You're reading the text anyway, so you are already aware of that. So look at Stu's examples, follow this example, work the problems, right? This stuff is good basic knowledge. Good basic knowledge. Think about this as being your antenna, right? You want to match your antenna, which has some impedance other than the characteristic impedance of the transmission line, to the transmission line impedance. So this is one way that you could possibly do that. Okay, so important general concepts here. Don't underestimate the value of this. Store all this information back in your mind. You may not remember the details, but you should remember essentially how these things work, and why you do them, right? Let's pay attention to why you do things. Don't just do things blindly and fumble around in a dark room. Pay attention to what you're doing, and ask questions. Why am I doing what I'm doing? Why is this important? All right. So a little motivational speech on this virus day. Hope everyone's well, and that'll conclude the lecture for the day.